When you step outside at night and look up, you are not seeing the universe as it exists right now. You're seeing a sky full of ghosts frozen in moments that have already passed. The nearest star, the brightest star, even our own sun are always slightly out of date. And every time someone drags a telescope into a backyard or fires up a billion-dollar observatory, they are doing the same strange thing. They are not just looking far away, they are looking back in time. If you want to keep travelling through that cosmic history with us, tap like and subscribe so you do not miss the next journey. So what are you actually looking at when you stare through a telescope? What moment is really hitting your eyes? Your brain wants to believe that the universe out there is happening in sync with the one down here. You see a star, you assume it is shining right now. You see a galaxy, you imagine it as a live feed. But the universe does not work that way, because the one thing that connects us to everything else out there, light, is fast, but not infinitely fast. Light has a speed that sounds absurdly huge by everyday standards, around 300,000 kilometers per second. That is so fast that a beam of light could circle Earth 7 times in the time it takes you to snap your fingers, yet the universe is so enormous that even at that ridiculous speed, light needs time to get anywhere. The bigger the distance, the bigger the delay. So every time you look up, you're not seeing things as they are, you're seeing them as they were by exactly however long their light took to get here. Let us start close to home. Aim a small telescope at the moon, and you are not seeing the moon as it exists in this exact moment. You're seeing it as it was about 1 and a bit seconds ago. Something impossible happened and the moon suddenly vanished. You would still see it hanging in the sky for a heartbeat and a bit, because its last photons are still on their way. 8 minutes for the sun, a little over 1 second for the moon. Our entire sense of the day sky is already slightly old news. Now push the telescope farther. Point it at Jupiter, the bright wandering dot that often dominates the night. Depending on where Earth and Jupiter are in their orbits, the light your telescope gathers left Jupiter between half an hour and almost an hour earlier. Whatever storms are raging in those clouds right now will not show up to you until tens of minutes later. Aim at Sirius, the brightest star in the night sky, and you are seeing a system 8.6 years in the past. Before some of you were even in high school, those photons started their journey. Stretch the distance again. Take any decent out-of-the-air telescope, or a space observatory like Hubble, and point it at the fuzzy smudge of the Andromeda galaxy. Every photon your detector or your eyes catch from that island of 1 trillion stars began its trip about 2.5 million years ago. When that light left, Earth was home to early human ancestors carving stone tools and trying to figure out fire. By the time it finally arrives at your telescope, your entire species has changed, migrated, built cities, invented the internet, and decided it wants to look back. So distance is not just distance. Distance is time. Farther away always means further back. The night sky is not a snapshot of a single cosmic moment. It is a patchwork of different eras layered on top of each other. The moon is 1 second old. Jupiter is dozens of minutes old. Nearby stars are years to centuries old. Distant galaxies are millions or billions of years old. When your eyes sweep across the sky, you are skimming through a history book written in light, jumping wildly from page to page without even realizing it. This is already weird at the level of naked eye stargazing. Telescopes take that weirdness and crank it up. A telescope does not just make things look bigger. Its real superpower is that it collects more light than your eye ever could. A bigger mirror or lens gathers more photons, which means it can see fainter, and therefore more distant objects. And more distant objects mean older light. A humble backyard telescope can already reach stars and galaxies whose stories began long before our species did. A giant observatory can watch the universe as it was when it was young. That is the quiet revolution telescopes created. Without them, the sky feels timeless. With them, we discover that time is baked into every beam of light. When Galileo first pointed his primitive instrument at the moons of Jupiter, he unknowingly turned himself into a historian of the cosmos. The rugged mountains on the moon that he sketched were not quite the moon of that moment. The tiny dots circling Jupiter were not quite the Jupiter of that moment. He was reading delayed messages, and so are we every time we upgrade our instruments. There is a second twist that makes this even more powerful. The delay is not random, it is perfectly predictable. You can measure a distance and know exactly how far back in time you are looking. That means telescopes are not just passive windows. Used cleverly, they become tools for doing history on a scale beyond anything we experience on Earth. Astronomers can choose which era of the universe they want to study by choosing how far away to look. Nearby for recent events, far away for deep time, all of it encoded in the same simple rule that light takes time to travel. In this video, we're going to lean fully into that idea. We will follow photons on their journeys, watch stars live and die in slow motion, see galaxies grow up, map an invisible cosmic web, and peek as close as we can to the beginning of everything. And underneath every beautiful image, every spectrum, every graph, the same quiet truth will be running in the background. Telescopes are time machines, not in the science fiction sense where you step inside and vanish. In the real sense where you sit very still, collect ancient light, and let the past come to you. If you strip away all the fancy telescope hardware and all the cosmic drama, the entire idea of looking back in time comes down to one simple fact. Light takes time to move, not much time on small scales, a lot of time on big ones. That is the whole trick. Every observation is really an answer to a quiet question in the background. How long did this photon have to travel before it ran into me? Once you get used to thinking that way, distance stops being just distance. It automatically turns into time. So what is this light that keeps showing up late to the party? In physics terms, it is an electromagnetic wave, one tiny vibrating patch of electric and magnetic fields sprinting through space. In human terms, it is the thing that lets you see anything at all. The speed of light in a vacuum is about 300,000 kilometers every second. That number is big enough that your intuition gives up, so it helps to break it into steps your brain can handle. Imagine shining a flashlight sideways around Earth. In 1 second, that beam could go around the planet 7 times. In the time it takes you to blink, light could travel from Earth to the Moon and most of the way back again. In 1 minute, light crosses a distance that would take a commercial jet tens of years of non-stop flying. So on human scales, light feels instant. When you flip a switch in your room, the delay before you see the bulb glow is so tiny your senses cannot detect it. But space does not care about human scales. Even the distance from Earth to the Sun is enormous compared to our everyday world. That gap is about 150 million kilometers. For light, that means roughly 8 minutes in transit. That is why we often call it 8 light minutes. It does not matter what wavelength you use. Visible light, radio waves, X-rays, they all obey the same speed limit in a vacuum. When you look at the Sun with proper protection, you are seeing the Sun as it was 8 minutes ago. Move outward again. The outer planets turn the delay from minutes into hours. Depending on the orbital dance, light from Jupiter might take half an hour or nearly an hour to reach you. Saturn pushes it even further. A radio signal sent to a spacecraft near Saturn and then echoed back can take well over 2 hours for the round trip. Control teams on Earth are effectively speaking to the past and waiting for answers from the future every single time they press a button. Distance and time are locked together. Once you leave the solar system, the kilometers become so ridiculous that astronomers give up and change units. Instead of counting steps, they start counting years of light travel. A light year is not a time in this context. It is a distance. It is how far light gets if you let it run for 1 full year. That works out to about 10 trillion kilometers. Say it fast and the number feels meaningless, but the key idea is that a light year automatically includes a built-in delay. 1 light year away means 1 year in the past. Take our nearest stellar neighbour, Proxima Centauri, is a little over 4 light years away. The red glow you would collect from it tonight left that star more than 4 years ago. If an alien civilization there switched their star completely off yesterday, every telescope on Earth would keep insisting everything is normal for another 4 years. Sirius, the bright beacon in the winter sky, sits roughly 8.5 light years away, which means you're always seeing it about 8.5 years late. Scale up again to the neighbourhood of bright stars and you are already swimming in time. A star 30 light years away is 30 years behind. 100 light years means 1 century of delay. The star might already have evolved, swelled up or exploded without us knowing. If some future telescope images a planet with possible signs of life 100 light years away, it will be showing us that world as it was when your grandparents were young, not as it is on the day you see the image. Galaxies take this idea and stretch it across billions of years. Aim a telescope at the Andromeda Galaxy and you get light that left when early humans were just learning how to survive the ice ages. Look at a galaxy 100 million light years away, and you are seeing the universe when dinosaurs had already vanished and mammals were slowly taking over Earth. Point a powerful space telescope at a galaxy 10 billion light years away, and the light hitting its detectors left when the universe itself was only a small fraction of its current age. Telescopes become records of different cosmic eras stacked on top of one another. The wild part is that you do not have to build a special machine to make this happen. The delay is not something astronomers turn on. It comes free with the structure of reality. The speed of light sets a maximum pace at which information can move, so whenever you see something distant, you're forced to see its history. Telescopes simply exploit that rule by collecting more and more of those delayed photons. Bigger mirrors, better detectors, longer exposures. All of it is really a way of digging deeper into the past by reaching farther into space. There is a natural question that comes out of this. If distance is the same as look-back time, is there a farthest time we can possibly see? Is there a moment where the universe stops sending us light altogether? The answer is yes, and that boundary will turn out to be one of the most important ideas in modern cosmology. To reach it, though, we first need to understand what happens to light during the unimaginable journeys that last millions or billions of years, and why the universe does not simply scramble those ancient messages beyond recognition. Picture a single photon leaving the surface of a distant star. It pops free of boiling plasma, punches through layers of gas, escapes the star's gravity, and then spends the rest of its life doing one thing, moving in a straight line at the speed of light. For thousands or millions or billions of years, nothing about it changes randomly. No cosmic vandal reaches in and scrambles its message just for fun. That stability is the only reason astronomy works at all. But the photon's journey is not completely clean. The universe does not just sit there while it flies. Space stretches, dust floats, gravity bends, and our own atmosphere adds a final layer of chaos right at the end. Start with the weirdest part. Space itself is expanding. On the largest scales, galaxies are not really flying apart through empty nothing. The emptiness between them is growing. When a photon travels through this stretching fabric, its own wavelength stretches along with it. The peaks and troughs of its electromagnetic wave get pulled farther apart. To us, that shows up as a shift toward redder colours, which we call redshift. The farther a photon has travelled through expanding space, the more its colour is shifted. Distance and time are written directly into its wavelength. Astronomers do not just stare at colours and guess. They use spectroscopy, which is a fancy way of saying they spread light out into a detailed rainbow and look for fingerprints. Atoms and molecules absorb and emit light at very specific wavelengths. Hydrogen, helium, oxygen, all of them leave recognizable patterns of bright and dark lines in a spectrum. Nearby, those lines appear at well-known positions. In light from a distant galaxy, the same pattern is shifted toward longer wavelengths. Measure how far those lines have slid, and you know how much the universe has expanded while the photon was on the road. That tells you both how far away the source is and how long ago the photon left. On top of all that stretching, the photon also has to dodge dust. Interstellar dust grains are tiny, often smaller than smoke particles, but there are so many of them spread through galaxies that they matter. Dust does not treat all light equally. Shorter wavelength blue light gets scattered and absorbed more easily than longer wavelength red and infrared light. It is the same basic physics that makes Earth's sky blue and sunsets red. When photons from a distant star or galaxy pass through dusty regions, the bluer ones are more likely to be knocked off course or absorbed entirely. The survivors that reach your telescope are biased toward the redder side. If astronomers ignored this, they would misjudge everything. Distant objects would look dimmer and redder than they really are, which could make them appear older, cooler or farther away than they actually were when they sent their light. So telescopes do not just observe at one wavelength, they look across a whole range, from ultraviolet through visible into infrared. By comparing how bright an object is at different wavelengths, astronomers can model how much dust it must have passed through and correct for that reddening. In infrared light, you can often see straight through dust clouds that look totally opaque in visible light, revealing stars and structures that would otherwise stay hidden. Then there is gravity, which does something both subtle and dramatic. According to Einstein's general theory of relativity, mass tells space how to curve, and curved space tells light how to travel. That means a photon passing near a massive object does not move in a perfect straight line. It follows a bent path through warped space-time. When the mass is something huge like a galaxy cluster, the bending can be strong enough that light from a background galaxy is stretched into long arcs or even split into multiple images. This effect is called gravitational lensing, because the cluster acts like a natural lens in space. From the photon's point of view, nothing magical happens. It just follows the straightest possible path in a curved geometry. From our point of view, the result is wild. One galaxy may appear as several separate smears around a foreground cluster. Each smear is light that left the same object at almost the same time, but took different curved paths and arrived at slightly different moments. Those extra travel times can be days, weeks, or even years apart. By measuring those delays and the way the images are stretched, astronomers can map how mass, including invisible dark matter, is distributed in the lensing cluster. The photon that began as a simple message about a remote galaxy now also carries a record of the gravity it passed near. Not every photon takes such a scenic route. Many travel through relatively empty intergalactic space, experience only gentle stretching from cosmic expansion, and arrive in a more or less direct line. Others get scattered by dust and never reach any telescope at all. Some are absorbed and re-emitted at longer wavelengths, changing their story along the way in controlled, understandable ways. The key point here is that the universe does not mangle photons randomly. It alters them through a few well-understood processes. Stretching and expanding space, a scattering and absorption in dust and gas, bending in gravitational fields. Then right at the end of their journey, our own planet throws one last obstacle in the way. Earth's atmosphere is great if you like breathing, but it's not great if you are a photon trying to deliver a pristine message from a distant galaxy. Turbulent air of different temperatures and densities makes starlight wiggle and smear as it passes through. To your eyes, this shows up as twinkling. To a telescope, it shows up as a constant blurring and shimmering of images. Water vapor and other molecules in the air absorb specific wavelengths, carving gaps out of the spectrum. And light pollution from cities adds a fog of unwanted photons that drown out the faint ones from deep space. Ground-based observatories fight back with clever tricks, which we will dive into more later. Adaptive optics systems use bright stars or artificial laser guide stars as references to measure how the atmosphere is distorting incoming light from moment to moment. Deformable mirrors then flex hundreds of times per second to cancel that distortion, sharpening the view. Telescopes are built on high, dry mountaintops where the air is thinner and steadier, and where fewer human lights glow nearby. Even so, the cleanest possible views come from space observatories like Hubble or the James Webb Space Telescope, which sit above the atmosphere altogether. Their detectors catch photons that have finally completed their journey without those last milliseconds of atmospheric chaos. Put all of this together and you get a surprisingly elegant picture. A photon leaves a source carrying information about that source. Its wavelength, its direction, its timing all encode what was happening when it was emitted. On the way, expanding space stretches its wavelength. Dust selectively dims and reddens it. Gravity may deflect and delay it. And our atmosphere might blur it at the final moment. None of this is random noise. Each step adds new layers of information that can be decoded with the right instruments and models. When a telescope catches that photon, it is not just seeing where and when it came from, it is also reading the history of the path it took. In the next chapter of our journey, we will look at how humans have built better and better eyes to catch these fragile messengers. Bigger mirrors, more sensitive detectors, clever optical tricks, and massive data pipelines. All of them designed for one purpose: to catch more ancient photons, understand how their journeys changed them, and turn those changes back into a clear picture of the universe as it was long before we were here to look. If light is the message, then telescopes are the mailboxes. Their job is brutally simple: catch as many photons as possible and put them in the right place. But doing that across billions of years of travel through a turbulent atmosphere with detectors that need to be almost impossibly sensitive turns into one of the most extreme engineering challenges humans have ever taken on. The story of modern astronomy is really the story of how we learned to build better and better eyes for the sky. The most important part of a telescope is not the fancy electronics or the sleek dome. It is the big piece of glass or metal that collects light. The primary mirror. Think of it as a bucket for photons. The larger the diameter of that bucket, the more light it can catch every second. And here is the crucial trick. The light gathering power does not grow linearly with size. It grows with the area of the mirror. Double the diameter and you get 4 times the area, so 4 times the light. Triple the diameter and the area jumps by a factor of 9. That is why astronomers are obsessed with bigger mirrors. A small backyard telescope might have a mirror the size of a dinner plate. A professional observatory mirror can be 8 meters across or more. The difference is not subtle. A giant mirror can collect enough light from a faint distant galaxy in a single night to reveal delicate structure and colour, while a small telescope would see nothing at all but noise. Every extra photon caught is one more piece of the universe's past we get to decode. Of course, nature is not generous about this. Building a single solid mirror much larger than about 8 meters is a nightmare. Glass sags under its own weight. Temperature changes cause it to expand and contract. You cannot just pour a bigger disk and hope it holds its perfect shape while you tilt it at the sky. Past a certain size, the mirror would warp, crack, or become impossible to support without distorting it. So engineers changed tactics. Instead of one enormous piece, they learned to build mirrors out of many smaller ones. Segmented mirrors are like high-precision mosaics. Dozens or even hundreds of hexagonal tiles are polished to nearly perfect shapes, then mounted so that together they act like one giant mirror. Each segment can be nudged, tilted, and flexed independently by actuators underneath it. Sensors watch how the segments line up and tiny motors correct any misalignment in real time. This technique lets telescopes like the James Webb Space Telescope and the extremely large telescope under construction in Chile reach diameters that would be impossible with a single slab. The mirror becomes not a static object but a living surface, constantly adjusted to stay in perfect focus. Even with a perfect mirror, ground-based telescopes have to deal with Earth's atmosphere smearing and wobbling the images. That is where adaptive optics comes in, which is one of the most clever inventions in modern astronomy. The idea is simple in principle. You look at a known point of light, figure out how the atmosphere is distorting it, then flex a small mirror to cancel that distortion before the light reaches your camera. In practice, it is wild. Telescopes use bright stars as reference points, or they create artificial ones by shining powerful lasers into the sky to excite atoms high in the atmosphere. A sensor records how that reference point blurs and wriggles thousands of times per second. That pattern tells a computer exactly how the air is bending the incoming wavefront of light. A thin, flexible mirror downstream, dotted with actuators, then changes shape in the opposite way. The distorted wavefront hits a distorted mirror and, if everything lines up, comes out smooth again. The result is that stars which were smeared into fuzzy blobs suddenly snap into sharp points, almost as if you had lifted the telescope out of the atmosphere and into space. Big observatories lean hard on this trick. The twin Keck telescopes in Hawaii, each with 10-meter segmented mirrors, and the very large telescope in Chile, made of 4 8-meter units, both use adaptive optics to reach resolutions comparable to, or even better than, space telescopes at some wavelengths. In images of star clusters, crowded galactic centers, or disks around young stars, the difference between having adaptive optics on or off is like the difference between looking through frosted glass and looking through a freshly cleaned window. Catching photons is only half the problem. You also need a way to record them efficiently. Early astronomers used the most advanced detector available at the time, their own eyes. The eye is sensitive, but it forgets almost instantly. You can only integrate light for a fraction of a second before the image fades. Photographic plates came next, letting telescopes collect light for hours onto a piece of glass coated with chemicals. That was revolutionary, but chemically based plates are terribly inefficient. They might capture only about 1 photon out of 100 that hit them. Modern telescopes use electronic detectors such as charge-coupled devices, which are essentially grids of tiny photon traps. When a photon lands in 1 pixel, it knocks an electron loose. Electronics then count those electrons and turn them into an image. These devices can capture well over 90% of the photons that reach them. That means the same telescope, with a modern detector, can see much fainter objects than it ever could with film. A single photon from a galaxy 10 billion light-years away arrives as a tiny blip in 1 pixel. A telescope might sit on that patch of sky for many hours, collecting millions of such blips until the accumulated signal rises out of the noise and an image appears of something so faint that no human eye could ever see it directly. To pull even more information out of that light, astronomers bolt spectrographs onto their telescopes. Instead of forming just a picture, a spectrograph spreads the incoming light into many wavelengths, like a detailed rainbow smeared across a detector. Each star or galaxy then becomes not just a point of brightness, but a set of lines and curves that encode its temperature, composition, motion, and distance. Gratings or prisms perform the separation, and careful calibration tells you exactly which pixel corresponds to which wavelength. This is how telescopes turn ancient photons into measurements rather than just pretty pictures. There is one more step in building better eyes that feels almost like cheating. If you cannot build a single enormous telescope, you can pretend you have one by linking many smaller ones together. That is interferometry. Instead of one giant mirror, you have multiple telescopes spread out over some distance. They collect light from the same object and send it to a central system that combines the signals. By measuring how the light waves from each telescope line up or interfere with one another, you can reconstruct details that would normally require a mirror as large as the separation between them. In the infrared and visible, arrays like the Very Large Telescope interferometer can combine the light from several big telescopes to reach the resolving power of a single instrument more than 100 meters across. In radio, the effect is even more dramatic. The Event Horizon Telescope linked radio dishes across Earth to create a virtual telescope the size of our planet. That is how we got the first direct images of black hole shadows. No one carved a mirror thousands of kilometers wide. They just learned to make distant antennas act like parts of one giant eye. Behind all these tricks, it's a final silent partner: data processing. A deep exposure from a space telescope can contain hundreds or thousands of galaxies, each one a collection of millions of photons spread over many pixels, each one redshifted, reddened, and slightly distorted. Software finds the objects, measures their brightness, shapes, and spectra, and catalogues them. Machine learning tools are now trained to recognize galaxies, stars, quasars, and oddities automatically, because there are simply too many for humans to inspect by hand. The hardware catches the photons. The algorithms turn them into knowledge. Together, giant segmented mirrors, adaptive optics, ultra-sensitive detectors, spectrographs, interferometer arrays, and powerful computers all serve a single purpose: to squeeze every possible bit of information out of ancient light that has crossed an expanding, dusty, curved universe to reach us. In the next part, we will throw those sharpened eyes at the oldest light of all, the faint afterglow from the early universe itself, and see how far back in time telescopes can truly reach before light simply runs out. If distance equals time, a dangerous question pops up sooner or later. If we keep looking farther and farther away, does the universe eventually run out of things to show us? Is there a final page in this cosmic history book, a last moment written in light beyond which everything is permanently hidden? The answer is yes. There is an edge, not of space but of time, and every optical or infrared telescope humanity has ever built is racing toward that same wall. To understand that wall, you have to imagine a universe that looks nothing like the one you know. Today, space is mostly transparent. Light from stars and galaxies can travel for billions of years with only occasional bumps on the way. Wind the clock back to the very early universe, and you get something completely different. The cosmos was hot, dense, and packed with charged particles. Electrons and atomic nuclei moved through a seething plasma, and photons could barely travel a step before smashing into something and scattering. In that early phase, the universe was glowing, but it was not see-through. Light could not travel long distances without being redirected. It was like trying to see across a room filled with thick fog or glowing steam. Everything was lit, but nothing was clear. Then, as the universe expanded, it cooled. After a few 100,000 years, the temperature dropped to the point where electrons could finally settle down and bind with nuclei to form neutral atoms. Hydrogen and helium stopped acting like free charges and started acting like actual atoms. The moment that happened, something dramatic changed. With far fewer free electrons around to scatter them, photons suddenly gained the freedom to cruise. Light that had been trapped in a dense fog was released into a universe that had just turned transparent. Cosmologists call this moment recombination. The glow from that epoch has been travelling ever since, stretching and cooling as the universe expanded, until today it fills the entire sky as a faint microwave background. That glow is the oldest light we can possibly see. It comes from when the universe was about 380,000 years old, which is incredibly young compared to its present age of roughly 13.8 billion years. Every telescope that observes the cosmic microwave background is looking at a baby picture of the universe. Not a galaxy, not a star. The whole universe, everywhere, at once. a single moment frozen into a shell of ancient light that now surrounds us. This background radiation was first detected in the 1960s by two engineers, Arno Penzias and Robert Wilson, using a radio antenna in New Jersey. They kept picking up a persistent hiss that would not go away. They cleaned the instrument. They chased down every possible source of noise, including actual pigeons living in the antenna and their droppings. The hiss remained. Eventually they realized they were hearing the afterglow of the early universe. A fossil light field that theory had predicted years earlier, now screaming quietly into their receiver from every direction. Since then, dedicated space missions have mapped this glow in exquisite detail. The Cosmic Background Explorer mission, often shortened to COBE, confirmed that the spectrum of this radiation matches what you would expect from a hot, dense plasma that has been stretched and cooled by cosmic expansion. The whole sky sits at a temperature of about 2.7 degrees above absolute zero, incredibly cold but still glowing just enough in microwave wavelengths. More importantly, COBE, and later the Wilkinson Microwave Anisotropy Probe known as WMAP, and the Planck satellite found that this glow is not perfectly uniform. It has tiny variations in temperature, only about 1 part in 100,000. Slightly hotter spots correspond to slightly denser regions in the early universe. Slightly cooler spots mark slightly emptier regions. Those tiny bumps are the seeds of everything. Over billions of years, gravity amplified those small differences into galaxies, clusters, and the entire cosmic web we see today. Telescopes that study the cosmic microwave background are not just taking a pretty picture of mottled static. They are reading encoded information about the contents and behavior of the young universe. The size and pattern of those temperature ripples tell us how much normal matter exists, how much dark matter, how much dark energy, and even whether the overall geometry of the universe is flat, open, or closed. From this single shell of ancient light, cosmologists have inferred that the universe is very nearly flat, that normal matter makes up only a small fraction of the total, and that dark energy dominates the large-scale behavior of cosmic expansion. This is where the hard limit appears. Before recombination, photons could not travel freely. Any light emitted earlier than that was scattered so many times that it lost any clear memory of where it started. There is no way for us to receive a clean beam from that opaque era in ordinary electromagnetic radiation. For telescopes that work with light, radio waves, infrared, ultraviolet, X-rays, and gamma rays, the cosmic microwave background is the ultimate wall. Beyond that, the universe is not just dark, it is hidden. You can think of it like looking into a foggy room from the outside. You can see the fog itself glowing and moving, but you cannot see the individual objects inside it. The cosmic microwave background is the glowing fog frozen at the moment it became transparent. Everything that happened before is etched into that pattern, but not visible as discrete points or structures. To appear earlier than that, we would need different messengers altogether, neutrinos that barely interact with matter, gravitational waves generated in the first fractions of a second after the Big Bang. These are topics for other kinds of observatories, different telescopes in a broader sense, tuned to different signals. For now, every electromagnetic telescope, from a small backyard radio dish to the most advanced space observatory, shares the same time horizon. It can approach 13.8 billion years ago, but never cross it. Webb can detect galaxies whose light set out only a few 100 million years after the Big Bang. Future instruments will likely push that back closer to the edge, finding some of the very first galaxies and perhaps signatures of the first stars. Yet there will always be a gap between time zero and the oldest light we can see. This limit is not a failure of technology. It is a feature of the universe itself. The cosmos simply did not allow light to travel freely before that time. When we look at the cosmic microwave background, we are seeing as far back in light as the universe will ever let us. Beyond that, if we want to know what happened, we have to infer it from this ancient glow and from non-light messengers that are only beginning to be explored. In the next part, we will step forward in time from that first clear snapshot and focus on individual stars. We will watch them form, live, and die, always with the same realization in the background. Every star you see is already a historical record. Some of them may have already exploded or faded, and telescopes are simply catching their last messages as they finally arrive. When you point a telescope at a star, it feels like you are catching it in the act, shining, pulsating, maybe flaring. But you're never seeing the life it is living right now. you're seeing a snapshot from years, centuries, or millennia ago, depending on how far away it is. Every stellar portrait is already an entry in the cosmic archive. And once you start to think of stars that way, the night sky stops being a flat wallpaper and turns into a layered record of birth, change, and death. Take Sirius, the brightest star in our night sky. To the naked eye, it looks like a single brilliant point. Through a telescope and with careful measurements, you discover it is actually a binary system. Sirius A, a bright star about twice the mass of the Sun, and Sirius B, a dense white dwarf. Light from this system takes about 8.5 years to reach us. That means when we watch Sirius B orbit, we are watching a collapsed stellar core as it was nearly a decade ago, slowly circling its companion, cooling and fading from a life that ended long before human history began. Move to Arcturus, a giant star about 37 light-years away. In a telescope it glows with a warm orange colour, the sign of a star that has left the main phase of its life and swollen into a red giant. There are photons reaching us now, left in the late 1980s. While we were inventing compact discs and early home computers, Arcturus was already in that evolved state. What it is doing today, right now at the star itself, is something our telescopes will not see until decades in our future. We are always a little behind. Then there is Betelgeuse, the famous red supergiant in Orion. Telescopes reveal not just a dot of light, but a huge, unstable star shedding gas into space. High-resolution images show bright and dark blotches across its surface and clouds of material blown off into surrounding space. Betelgeuse is close enough that when it eventually explodes as a supernova, it will be spectacular, briefly rivaling the full moon in brightness. But here is the unsettling part. That explosion could already have happened. Betelgeuse sits several hundred light-years away. If it blew up in the year 1500, the flash is still racing toward us. Until those photons arrive, our view shows a star that may already be gone. Telescopes do not just catch stars in midlife, they also study their corpses. White dwarfs like Sirius B are the exposed cores of stars that were once like the Sun, about the size of Earth, but with roughly the mass of the Sun packed into that volume, they glow from leftover heat and gradually cool over billions of years. Neutron stars are even more extreme. A city-sized ball of nuclear density spins so fast they can flash beams of radiation past Earth hundreds of times per second. Radio telescopes see them as pulsars, clocks so regular that tiny changes in their timing reveal gravitational waves and orbital decay. Some of the most dramatic stellar deaths leave behind glowing clouds that telescopes can track for centuries. The Crab Nebula is a famous example. In the year 1054, Chinese astronomers recorded a guest star that appeared in the sky, bright enough to see in daylight. What they witnessed was a supernova in our own galaxy, about 6,500 light-years away. The actual explosion happened around 4,500 years before that, but its light only reached Earth in the 11th century. Now telescopes show us the expanding debris, filaments of gas, and the central pulsar driving a wind of energetic particles. Each new image adds another frame to a movie that has been unfolding for thousands of years. Another modern landmark is supernova, 1987A in the Large Magellanic Cloud, a nearby small galaxy roughly 168,000 light-years away. When its light reached Earth in 1987, that star had actually exploded in the distant past. Long before human civilization took its current form, astronomers had archive images of that region from earlier decades. By comparing them, they identified the exact star that had vanished and exploded. That was the first time we could say with confidence this specific star died in this specific way. Telescopes have continued to monitor the remnant, watching rings of gas light up and expand. It is like watching a slow-motion replay of a stellar death that concluded long before any of us were born. Not all stellar stories end in a single dramatic blast. Planetary nebulae mark the quieter deaths of stars more like the Sun. As these stars run out of fuel, they puff off their outer layers in shells of gas that drift away at tens of kilometers per second. The exposed hot core, now a white dwarf, bathes this gas in ultraviolet light and makes it glow. The Ring Nebula and the Helix Nebula are classic examples. Telescopes resolve intricate details in these structures, knots, filaments, layered shells that tell us the star did not simply exhale once, but went through repeated spasms of mass loss. We see those episodes separated in space, which really means separated in time. Each shell is the frozen record of an event thousands of years ago. Variable stars add another layer to this time travel. Some stars pulsate regularly, swelling and shrinking in size, which makes their brightness rise and fall in a steady rhythm. Cepheid variables are one of the most important types. Their pulsation period is directly related to their true brightness. Measure how quickly they pulse, compare that to how bright they look, and you can work out their distance. That discovery turned these stars into cosmic yardsticks, helping Edwin Hubble show that distant spiral nebulae are actually other galaxies and that the universe is expanding. Many of these Cepheids have been monitored for over a century. Long-term records show tiny changes in their periods and amplitudes, revealing slow internal evolution that no single human lifetime could see on its own. Other variable stars are less regular but just as revealing. Mira, one of the first known long-period variables, waxes and wanes over many months, sometimes visible to the naked eye, sometimes disappearing entirely. Its behaviour has been recorded for more than 400 years. Each generation of telescopes adds more precise data, turning that light curve into a time series that spans many human lifetimes. When astronomers today compare new measurements to ones taken in the 17th century, they are literally comparing historical records of the same star, separated by centuries. Modern missions like the Gaia Space Telescope push this long view to a new level. Gaia has measured the positions and motions of more than 1 billion stars in the Milky Way with staggering precision. By tracking how those positions change over years, Gaia maps stellar orbits around the galaxy, reveals moving groups that were once clusters, and reconstructs past encounters. Combined with chemical fingerprints from spectroscopy, astronomers can identify ancient stellar populations that formed in different parts of the early Milky Way and were later stirred together. Your telescope is not just looking at where stars are, it is letting you rewind where they came from and how they drift through space. All of these techniques share one quiet truth. To understand stars, you have to embrace the delay. You watch Betelgeuse knowing it might already be gone. You measure Cepheid variables over many decades to see them evolve. You study supernova remnants as expanding shells that record different moments in a single explosion. Telescopes give us snapshots from different times in a star's life and death, and by comparing those snapshots, we turn their frozen histories into a continuous story. In the next part, we will zoom out from individual stars to their communities. Open clusters, globular clusters, stellar nurseries, and the chaotic neighbourhoods where stars are born, live in groups, and eventually drift apart. Once again, distance and time will work together, letting telescopes show us star formation and stellar recycling at different stages, all at once, across the galaxy. So far, we have treated stars mostly as solo artists, one here, one there, each living its own long, lonely life. Reality is messier and more interesting. Stars are social. They are born in crowds, grow up in loose neighbourhoods, join and leave groups, and eventually dump their ashes back into the same galactic streets that raised them. When you point a telescope at these communities, you are not just seeing individual stars frozen in time, you are seeing whole ecosystems caught at different stages of their long drama. Start with the stellar version of a kindergarten class, open clusters. These are loose groups of a few hundred or a few thousand young stars, all born from the same collapsing cloud of gas and dust. The Pleiades, that tiny dipper of blue stars in Taurus, is a classic example. Through a telescope you see bright hot stars blazing against faint wisps of reflection nebula, the leftover dust they have not yet swept away. The cluster sits a few hundred light years from us, which means every perfect postcard image of it shows the cluster as it was a few hundred years ago. The gas and dust patterns we see today are the preserved shapes of winds and radiation carved centuries in the past. Open clusters do not last. Gravity from the rest of the galaxy tugs at them. Close encounters between member stars slowly fling them apart. Over tens or hundreds of millions of years, the cluster dissolves into the general population of the Milky Way. Telescopes capture different clusters at different ages. Some are compact and repelled and wrapped in nebulae. Others are already stretching out, their brightest massive stars gone supernova, their surviving members drifting away. Every cluster you see is a snapshot of one family at one moment in a slow breakup. At the other extreme are globular clusters, the ancient city centres of the stellar world. These are dense, roughly spherical collections of hundreds of thousands or even millions of stars, packed into a region only a few dozen light years across. A telescope view of a globular cluster looks almost artificial, like someone spilled glitter into space. Messier 13 in Hercules is a famous one, hanging about tens of thousands of light years away. The stars inside are more than 10 billion years old. Their light left long ago, and even when it did, those stars were already ancient. Spectra of globular cluster stars show very few heavy elements. That tells you they formed early, before many generations of stars had time to enrich the cosmos with elements heavier than helium. When you observe a globular cluster, you are looking at a preserved fossil community from the young universe. The cluster's current motions around the Milky Way tell you about past mergers and collisions. Its stars carry chemical fingerprints of long-vanished environments. Telescopes turn these crowded swarms of dots into a time capsule of galaxy formation itself. Not all stellar groups are so tightly bound. Stellar associations are looser clouds of young stars that share a common origin and motion but are already spreading out. The Orion OB association, sprawling across the constellation Orion, is one of the best known. Through infrared telescopes you can see hundreds of hot young stars, pillars of gas and embedded protostars still wrapped in cocoons of dust. These associations are transient. Over tens of millions of years their members drift apart and become part of the general population. But for a while, telescopes catch them in the act of dispersing, giving us a snapshot of a star-forming region in its teenage years. Inside these associations sit the real nurseries, giant molecular clouds like the Orion Nebula or the Carina Nebula. In visible light, they appear as glowing clouds threaded with dark dust lanes. In infrared, they become crowded maternity wards. Telescopes pierce the dust and reveal clusters of newborn stars, jets of material blasting from protostars, and disks of gas and dust where planets are beginning to form. The light we see from those young stars left thousands of years ago. Any planet that has just assembled around them today is invisible to us until its light has had time to catch up. Dark nebulae tell the opposite story. These are cold, dense clouds that block background starlight, appearing as inky patches against the Milky Way. The Coalsack Nebula in the southern sky is a famous one. At visible wavelengths, it looks like an absence. In infrared, telescopes reveal that it's full of hidden stars and forming systems. The contrast between the two views is another reminder that what you see at any given wavelength is only one slice of a much richer history. Dust hides the drama until the right instrument arrives. Stellar graveyards are scattered throughout these same neighbourhoods. Planetary nebulae, supernova remnants, and wind-blown bubbles are not just pretty shapes, they are the direct evidence of how stars return their material to the interstellar medium. In images of the Helix Nebula or the Butterfly Nebula, each shell and lobe marks a separate event of mass loss. Ultraviolet light from the central white dwarf makes those shells glow. Telescopes essentially replay thousands of years of a star's dying breaths, encoded into expanding layers of gas. Supernova remnants like the Vela remnant or Cassiopeia push the scale up. Expanding shells of gas span dozens of light years. X-ray telescopes show shock-heated gas at millions of degrees. Radio telescopes map energetic electrons spiraling in magnetic fields. Optical telescopes trace filaments where the blast wave plows into surrounding material. Each wavelength sees a different stage in the same explosion. And because light travel time is built in, different parts of the shell we see now actually left at slightly different moments in the remnant's expansion. The whole thing is a three-dimensional time sculpture. Stellar motion adds another twist. Clusters do not just sit in place, they orbit the galactic center. Some are being pulled apart into streams, long ribbons of stars stretched along their orbital paths. Telescopes like Gaia have mapped these streams by measuring precise positions and motions of stars. The Hyades cluster, for example, is slowly dispersing. Its members are fanning out, but their shared motion in space reveals their common origin. When you look at a stream or a moving group, you're seeing the ghost of a long-dissolved cluster, its history written into the coordinated motions of its stars. Runaway stars offer more dramatic stories. These are stars flung to high speeds by gravitational encounters or by the explosion of a companion. They race through the galaxy at tens or hundreds of kilometers per second, ploughing into interstellar gas and creating glowing bow shocks ahead of them. Infrared images show arcs of compressed gas and dust where the star's wind slams into its environment. The shape of that bow shock and the position of the star tell you how long it has been running and how fast it is moving, turning a static picture into a clock. All of this recycling has a direct connection to you. The calcium in your bones, The iron in your blood, the oxygen in your lungs all came from earlier generations of stars that lived, died, and polluted their surroundings. Telescopes catch the raw process in action. They show you star-forming regions lit by young hot stars, supernova remnants rich in heavy elements, and clouds of gas that are slowly enriched over billions of years. When you see a reflection nebula shining pale blue from scattered starlight, you are watching the same dust that might one day collapse into new stars and planets, and perhaps new beings looking back out. In these stellar neighbourhoods, telescopes do what they do best. They turn distance into time. A young open cluster a few hundred light years away shows us stellar youth from a few centuries ago. A globular cluster tens of thousands of light years away shows us stellar populations from the dawn of the galaxy. Streams, bow shocks and nebulae record motions and eruptions that unfolded over millions of years. Put them together and you get not just a static map of where stars are now, but a layered story of how they are born, evolve, die, and feed the next generation. In the next part, we will zoom out even further, beyond individual neighbourhoods, beyond clusters, to entire galaxies. Spirals, ellipticals, mergers, and starbursts, all seen at different distances and therefore at different ages. We will use telescopes to turn the universe into a kind of living fossil record, where every galaxy we observe is a snapshot from a different chapter in cosmic history. If stars are the characters in our story, galaxies are the cities they live in. Each galaxy is a sprawling ecosystem of gas, dust, dark matter, and hundreds of billions of stars all evolving together. And just like with stars, telescopes never show us what a galaxy is doing right now. Every spiral, every glowing core, every faint smudge in a deep field is a fossil snapshot from some earlier chapter in the universe's life. Look at a lot of galaxies at a lot of distances, and you're not just making a map of where things are. You are watching the universe grow up. Let us start with our nearest big neighbour, the Andromeda Galaxy. In a small telescope, it appears as a hazy, elongated glow. In a large one, it explodes into a vast spiral with lanes of dark dust and clusters of bright blue stars. It sits about 2.5 million light years away, so every image we have of Andromeda shows it as it was when early humans on Earth were just learning to use stone tools. Since then, Andromeda's stars have orbited, some have died in supernovae, and others have formed. Its spiral arms have shuffled. None of that is visible to us yet. We are always 2.5 million years behind. The Triangulum Galaxy, a smaller spiral a bit farther at around 3 million light years, adds another data point. Sombrero sits tens of millions of light years out, an edge on a disk without a bright bulge and a thick dust lane. The Whirlpool Galaxy at roughly 23 million light years is a grand design spiral face-on with sweeping arms and pink star-forming regions. The Virgo cluster, filled with more than 1,000 galaxies, lies about 50 million light years away. Each of these systems lives in a different environment, but they share one thing. Their light left long before humans had cities, languages, or telescopes. Now stretch the distance harder. In deep exposures, big telescopes see galaxies hundreds of millions or billions of light years away. Some are neat spirals, some are smooth ellipticals. Many are oddly shaped, with warped disks and long tidal tails stretching out into space. Those tails are stars and gas flung out by gravitational encounters and mergers. When we see a pair of galaxies caught in mid-collision, like the Antennae galaxies around 45 million light years away, we are seeing a brief phase in a long process. Two spirals will eventually settle into one larger remnant. The snapshot we see is only one moment in a merger that takes hundreds of millions of years. Galaxies do not always behave politely. Centaurus A, about 13 million light years away, looks like an elliptical galaxy sliced through by a dark dust lane. Radio telescopes reveal huge lobes of emission blasting out from its core, driven by a supermassive black hole that is actively feeding. Messier 82, about 12 million light years away, is a starburst galaxy. Infrared images show tremendous amounts of warm dust heated by intense star formation. X-ray telescopes detect hot gas being driven out in a galactic-scale wind. You are seeing a galaxy in a brief, furious growth spurt. Different wavelengths reveal different sides of these galactic lives. Optical telescopes show stars and glowing gas. Infrared telescopes pierce dust clouds and expose hidden star-forming regions. Radio telescopes map cold hydrogen gas and the rotation of disks. X-ray telescopes pick up hot gas in cluster environments and around active black holes. The same galaxy can look calm in one band and explosive in another. When astronomers combine all these views, they get a more complete picture of what the galaxy was doing when its light set out. Colour turns out to be one of the simplest and most powerful clues. Blue galaxies are filled with young, hot, short-lived stars. That means they are currently forming stars at a good rate in the era we are seeing them. Red galaxies contain mostly older, cooler stars with little recent star formation. They have used up or lost much of their cold gas, so when a telescope captures a red elliptical galaxy a billion light-years away, you are looking at a system that had already shut down most of its star formation a billion years in the past. Survey many galaxies at many distances and patterns emerge. In the nearby universe, there are plenty of calm spirals and many red ellipticals with minimal ongoing star formation. Move your gaze to a few billion light-years away, and you find more bright blue disks and more galaxies in the process of merging. Go even deeper, out to 6 or 10 billion light-years, and the picture becomes chaotic. Many galaxies are clumpy, irregular, or compact. Some are furiously forming stars at hundreds of times the rate of the Milky Way today. Others host blazing active nuclei where supermassive black holes are swallowing gas and shining across the cosmos. This is not an accident. You are watching cosmic demographics change with time. Early on, the universe was smaller, denser, and richer in cold gas. Galaxies collided more often and had plenty of fuel to build new stars and feed their central black holes. Telescopes that reach those distances see a younger universe filled with messy, growing structures. As time goes on, gas gets used or blown out by winds and jets. Mergers become less frequent as the universe expands and galaxies drift farther apart. Nearby, in the recent past, we see more orderly spirals and quiet ellipticals. The wild teenage years are behind them. Galaxies at different masses also follow trends. Surveys show that the most massive galaxies form their stars early and then quenched, turning red first. Smaller galaxies often kept forming stars for much longer. This pattern, sometimes called downsizing, appears when you compare nearby dwarf galaxies, which can still be forming stars today, with giant ellipticals whose stars are mostly ancient. Telescopes did not just infer this from theory, they read it directly from the light. Stellar populations in those galaxies have spectral fingerprints that reveal their ages and metal content. Clusters and groups add another layer. Galaxies in dense environments like the Virgo cluster often look stripped and quenched. Their gas has been removed by ram pressure as they plough through hot intracluster gas, or by repeated encounters with neighbours. Field galaxies, which live in relative isolation, can keep their gas longer and form stars more steadily. By observing clusters at various distances, astronomers see how these environmental effects grow stronger over time. Again, distance becomes a time axis. Nearby clusters show the end result of billions of years of harassment. Distant ones show earlier stages when more spirals are still intact. All of this rests on the same foundation we have been building from the start. Light takes time to travel. A galaxy 1 billion light-years away is a 1 billion-year-old memory. A galaxy 10 billion light-years away is a 10 billion-year-old memory. Telescopes that can collect enough of that faint light and break it into spectra can reconstruct when its stars formed, how much dust it contains, how fast it is moving, and how it is shaped. Put millions of such memories together at different distances, and you get a moving picture of galaxy evolution that spans almost the entire history of the universe. So when you look at a famous Hubble or Webb deep field full of tiny coloured smudges, you're actually staring at a time stack. Some of those galaxies are relatively nearby and recent. Others are ancient fragments from when the universe was only a fraction of its current age. They appear together in one image, but they did not exist together in that form at one moment. Telescopes have layered them onto the same canvas by catching photons that left at very different times. In the next part, we will zoom out one more step beyond individual galaxies and local clusters to the largest patterns of all. We will see how telescopes map the cosmic web, reveal the hidden scaffolding of dark matter, and use the distortion of ancient light to show how structure has grown across billions of years. By now we have watched stars live and die and galaxies grow and collide. But all of that drama is still only the small-scale structure of the universe. If you zoom out far enough, galaxies themselves start to look like grains of dust and a new pattern appears. The cosmos is not a random spray of islands in a dark ocean. It is a vast network. Filaments, knots, and empty cavities form what astronomers call the cosmic web. And once again, telescopes are not showing us how that web looks today. They are showing us how it was woven across billions of years, all shaped by something we cannot see directly. The first hint of this web came when astronomers stopped treating galaxies as isolated curiosities and started counting them in 3 dimensions. A simple photograph of the sky only gives 2 coordinates, up, down, and left, right. To turn that into a real map, you need distance for each galaxy. That is where redshift comes in. As we saw earlier, the expansion of the universe stretches light. The more distant a galaxy is, the more its spectral lines are shifted toward the red. Measure that shift, and you get not just a speed, but an approximate distance and therefore an approximate look-back time. Surveys like the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey use dedicated telescopes to record spectra for hundreds of thousands and eventually millions of galaxies. Each galaxy became a dot in a 3-dimensional map. When you plot those dots, they do not fill space evenly. They arrange themselves into long, thin filaments that intersect at dense knots where clusters of galaxies sit. Between those structures lie enormous voids, regions many tens of millions of light-years across that contain very few galaxies at all. On these scales, the universe looks like froth. Imagine the pattern of bubbles in a sink full of soap, thin walls, thicker junctions, and mostly empty interiors. The difference is that here the walls are chains of galaxies and the junctions are giant clusters. When telescopes look at galaxies a few billion light-years away, they see a version of this pattern that is still growing. Look closer to home, and the filaments and voids have stretched and merged further. Distance translates into time again. The cosmic web you see in any particular survey is a frozen frame from the ongoing movie of structure formation. What sculpts this web? Normal matter alone is not enough. If you take the amount of visible gas, dust, and stars into the universe and let it collapse under its own gravity in a simulation, you do not get the right pattern. The filaments are too weak, the clusters are too small, the timing does not match. To make the maps that telescopes produce, you need a lot more mass than we can see. That extra mass behaves as if it does not interact with light at all. It simply provides gravity. We call it dark matter, not because it is spooky, but because it neither emits nor absorbs light in any detectable way. Computer simulations that include dark matter show something striking. Start with a nearly uniform early universe, sprinkle in tiny variations in density like the ones measured in the cosmic microwave background, and let gravity run for billions of years. Dark matter clumps along invisible filaments. Gas falls into those clumps, cools, and forms stars. Galaxies assemble where dark matter halos are densest. Clusters grow at the junctions of filaments as halos merge. When you compare the final simulated web to real galaxy surveys, the match is surprisingly good. Telescopes are essentially confirming that most of the mass that shaped history is invisible. There is another subtle pattern stamped into this web. In the early universe, before recombination, sound waves rippled through the hot plasma. Regions of compression and rarefaction left a preferred separation scale between matter over densities. These are called baryon acoustic oscillations. Later, when galaxies formed, they inherited that preferred spacing. When you measure how galaxies cluster today at different redshifts, you find a small excess of pairs separated by that specific distance. That distance acts like a standard ruler. By seeing how its apparent size changes with redshift, telescopes can track how fast the universe has expanded at different times and test models of dark energy. Galaxies in these maps are not just sliding along with the smooth expansion. They also fall toward overdense regions and drift away from voids. These extra motions are called peculiar velocities. They distort redshift measurements slightly. In dense regions, galaxies appear to line up in stretched fingers pointing toward us or away from us. On larger scales, coherent flows toward massive structures squash clustering patterns along the line of sight. These redshift space distortions encode how quickly structure is growing. Measure them at different distances, and you are literally watching gravity build the cosmic web over time. Telescopes have another way to map the invisible. Gravitational lensing does not just produce pretty arcs and multiple images around massive clusters. It also creates subtle distortions in the shapes of countless background galaxies. Each one is stretched a tiny bit by the mass lying between us and it. No single galaxy tells you much, but if you analyze millions of them statistically, you can reconstruct how matter is distributed in front of them. This is called weak gravitational lensing. Wide-field surveys use weak lensing to build maps of dark matter directly, without relying on how bright or massive galaxies are. The pattern of these distortions, often called cosmic shear, shows how clumpy matter has become at different times. By slicing the background galaxies into distance bins, you can see how the clumpiness changes with redshift. That history is sensitive to both dark matter and dark energy. If gravity behaved differently on large scales, or if dark energy changed its behavior with time, the growth of structure would leave a telltale signature in these maps. On smaller scales, a related technique called galaxy-galaxy lensing measures how individual galaxies sit inside their dark matter halos. You take many foreground galaxies, stack the weak lensing signal from background sources around them, and infer the typical mass of their invisible halos. Do this for different galaxy types and at different distances, and you learn how halos and their galaxies co-evolve. Again, telescopes are not directly seeing dark matter. They are seeing how it bends the path of photons from older light behind it. Galaxy clusters are particularly powerful laboratories. They are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, hot gas that glows in X-rays, and an even larger reservoir of dark matter. Telescopes attack cluster mass from several angles. X-ray observations measure the temperature and distribution of the hot intracluster gas, which depends on the cluster's gravitational well. Optical and radio lensing reveal how the cluster bends light from background galaxies, mapping total mass regardless of what form it takes. The motions of member galaxies reveal mass through their speeds. Another technique, the Sunyaev-Zeldovich effect, uses the cosmic microwave background as a backlight. Photons from that ancient glow pass through hot gas in clusters and gain a bit of energy through scattering. This leaves a tiny distortion in the spectrum of the background when you look in the direction of the cluster. Radio and microwave telescopes can detect that distortion. Its strength depends on how much hot gas is there, which in turn traces the cluster's mass. Since this effect does not fade with distance the way light does, it is a powerful way to find clusters even very far away in time. When all these measurements agree, they give us confidence in our picture. Cluster masses inferred from X-rays, lensing, dynamics, and the Sunyaev-Zeldovich effect generally line up, within uncertainties. That consistency tells us that the same gravity that governs falling apples is shaping galaxy clusters billions of light years away. It also tells us that the amount of dark matter required to explain galaxy rotation curves, gravitational lensing and large-scale clustering is roughly the same. Different messengers, same invisible scaffolding. If you step back and look at the full story, it becomes almost eerie. Telescopes record the positions and shapes of galaxies whose light left when the universe was young. Those patterns reveal a vast web of structure. Simulations fed with dark matter and gravity reproduce that web across billions of years. Independent techniques like lensing and cluster studies confirm that most of the mass in that web does not glow. We have never seen dark matter directly, but we see its fingerprints everywhere in the way light from the past arrives. In the next part, we will take this cosmic web and add the element of time even more explicitly. We will follow how star formation rates rose and fell, how galaxies changed shape and colour, how quasars ignited and faded, and how the whole universe went through a wild youth before settling into the quieter state we see nearby. Once again, telescopes will be our time machines, turning distance and faint old light into a story of the universe growing up. By now we have maps of the cosmic web, star-forming nurseries, quiet ellipticals and violent mergers. All of them are frozen at different times in the past. The real magic happens when you put those snapshots in order. Telescopes do not just show us a big universe filled with stuff. They show us a universe that changes, with a childhood, a wild adolescence, and a calmer middle age. We can literally chart when stars were being born the fastest, when black holes were partying hardest, and when everything started to slow down. One of the simplest ways to tell this story is to ask a blunt question. At any given cosmic time, how many new stars were forming? Take galaxies at similar distances, which means similar look-back times, measure how many stars they are making every year, and then repeat this for many different distances. When astronomers did this with deep surveys, they found something surprising. Star formation in the universe is not steady. It rose, peaked, and then declined. There was a time when the universe was much busier at making stars than it is today. If you roll the clock back to when the universe was only a few 100 million years old, you see the first known galaxies. They are small, irregular, and forming stars fiercely relative to their size. Push forward to about 3 to 4 billion years after the Big Bang, and things get extreme. This era, often nicknamed cosmic noon, is when star formation across the universe reached its maximum. Galaxies were turning gas into stars at rates 10 times higher than the Milky Way manages today, and some were hundreds of times more intense. Telescopes looking at galaxies 6 to 10 billion light-years away are seeing that boom time directly. After cosmic noon, the party slowly winds down. As telescopes shift their gaze to nearer galaxies, which means later times, they see the average rate of star formation decline. Massive galaxies shut down first, their gas is consumed, heated, or blown out by supernova winds and black hole activity. Smaller galaxies keep forming stars longer, but even they fade with time. By the present day, the universe is a much quieter place in terms of star birth. We live in the afterglow of a once frantic era. Morphology, the overall shape and structure of galaxies, changes along with this. When telescopes peer very far back to early times, most galaxies look messy. Many are clumps, chains, or irregular blobs with multiple bright knots of star formation. Clear spiral arms and clean elliptical shapes are rare. Move to intermediate distances, a few billion light-years away, and you start to see familiar forms emerge. Some galaxies develop early spiral patterns. Others puff up into more rounded shapes. Closer still, in the nearby universe, grand spirals with well-defined arms and smooth ellipticals dominate. The universe went from a chaotic, clumpy place to one where galaxies settled into more regular architectures. Mergers played a huge role in that transformation. Telescopes catch many galaxies in the act of colliding at moderate and high redshifts. Long tidal tails, distorted disks, and double cores give them away. These collisions trigger bursts of star formation and can funnel gas into central black holes. Over time, repeated mergers build up massive ellipticals and transform disk galaxies. Farther back in time, mergers are more common, simply because the universe was denser and galaxies were closer together. Today, big mergers still happen, but less often. Our own Milky Way is on a slow-motion collision course with Andromeda, but their first real encounter is still billions of years in the future. Quasars add another layer to this timeline. A quasar is a galaxy whose central supermassive black hole is actively feeding on gas, shining so brightly that it can outshine the entire host galaxy. In the nearby universe, quasars are rare. Most big black holes are quiet, with only a trickle of material falling in. When telescopes look back 6 to 10 billion light-years, quasars explode in number. This was the age when central black holes were gulping gas at furious rates. Their jets and radiation lit up the cosmos and helped shape their surroundings. Push even closer to the Big Bang and quasars become rare again, because there has not yet been enough time to grow very massive black holes. This rise and fall of quasar activity lines up with galaxy growth. Young galaxies at cosmic noon are rich in cold gas. That gas feeds both star formation and black hole accretion. As gas is consumed or expelled, both processes slow. By measuring how many quasars and how many starburst galaxies exist at different distances, telescopes show that galaxies and their central black holes co-evolved. They grew up together, then calmed down together. Chemical evolution rides on top of all of this. Every generation of stars forges heavy elements in its core and returns them to space through winds and explosions. Telescopes measure the abundances of these heavy elements, which astronomers call metals, through spectral lines. Light from very distant galaxies shows relatively weak metal lines. Their gas is mostly hydrogen and helium, with only small traces of carbon, oxygen, and heavier elements. Closer galaxies show progressively stronger metal lines. Their gas has been cycled through more generations of stars. By the time you get to the present-day Milky Way, stars like the Sun contain a rich mixture of heavy elements that make planets and life possible. The same story plays out in individual stars within our own galaxy. Some old halo stars, observed with large telescopes and high-resolution spectra, have extremely low metal content. They are fossils from the early universe, formed before much enrichment happened. Young stars in the disk of the Milky Way are metal-rich, the end result of billions of years of stellar recycling. Light from these stars encodes when they formed relative to the universe's chemical history. Even cosmic structure on the largest scales carries a timeline. In the very early universe, as recorded in the cosmic microwave background, matter was nearly smooth, with tiny ripples. Over billions of years, gravity amplified those ripples into filaments, walls, and voids. Galaxy surveys at different redshifts show that growth in progress. At high redshift, filaments are shorter and clusters are smaller. At low redshift, filaments have stretched, clusters have merged, and voids have swollen. Weak lensing maps of dark matter confirm that clumpiness has increased with time in a way that matches our models of dark matter and dark energy. Tie all of this together, and you get a surprisingly coherent biography. The universe began hot and nearly smooth. The first stars and galaxies lit up a few 100 million years later and rionized the hydrogen fog. Star formation ramped up to a peak around 10 billion years ago and then declined. Galaxies grew from chaotic clumps into well-structured spirals and ellipticals, with mergers and feedback sculpting them. Central black holes went through their own hyperactive youth as quasars and then settled down. Heavy elements accumulated steadily, making rocky planets and complex chemistry possible. All of that is not guesswork scribbled on a chalkboard. It is written in light that telescopes catch from different distances, which means different times. In the next part, we will shift from the grand storyline back to specific turning points in our own understanding. We will look at how telescopes, acting as time machines, led to some of the biggest discoveries in modern cosmology, from the expansion of the universe to the shocking realization that that expansion is accelerating, driven by something we still barely understand. By this point, telescopes are clearly time machines, but they are also something else. They are devices that have repeatedly forced us to admit that our story of the universe was wrong and needed to be upgraded. Every time humanity thought it had the big picture mostly sorted out, some patient telescope quietly gathered ancient light and handed us a plot twist. Expansion, dark matter, dark energy, gravitational waves, planets everywhere. None of that was obvious from Earth's surface without a very long look back in time. Take expansion. For a long time, many scientists assumed the universe was static on the largest scales. Stars move, sure, but the grand cosmic stage itself was thought to be unchanging. That picture shattered when Edwin Hubble and his collaborators used a large telescope on Mount Wilson in the 1920s to study fuzzy spiral nebulae. By finding Cepheid variable stars in those spirals, he turned them into distance markers and proved they were entire galaxies far beyond the Milky Way. Then came the second blow. When Hubble measured the spectra of those galaxies, he found their light was systematically shifted toward the red. The farther away a galaxy was, the bigger the shift. That relation between distance and redshift meant the galaxies were not just drifting randomly. Space itself was expanding, stretching the light as it travelled. Telescopes had turned dim smudges into evidence that the universe was not a static backdrop, but something that had a past and was changing. Every galaxy in his plots was a messenger from a different moment in that history. Decades later, another telescope-driven surprise arrived. By the 1990s, most cosmologists expected that cosmic expansion should be slowing down under the pull of gravity. Two independent teams set out to test this by observing distant Type 1a supernovae, special exploding stars that can be used as standard candles. Measure how bright they look compared to how much their light is redshifted, and you can reconstruct how fast the universe was expanding when the light left them. The result was the opposite of what everyone expected. Those distant supernovae looked dimmer than a slowing universe would allow. That meant they were farther away than they should have been if expansion had been constant or decelerating. The only consistent explanation was that expansion had sped up. Something in the fabric of the cosmos was pushing galaxies apart more and more strongly over time. We gave that something a name, dark energy, but we still do not know what it is. What we do know is that discovering it required telescopes capable of catching the pale flicker of exploding stars billions of light years away, and treating each one as a clock from the deep past. The cosmic microwave background told a different part of the story. Radio telescopes discovered its existence in the 1960s as a faint hiss that would not go away. Later space missions mapped it across the entire sky. Those maps turned out to be a goldmine. Tiny temperature variations frozen into that ancient light revealed the density, age, and geometry of the universe with astonishing precision. By reading those patterns, cosmologists learned that normal matter is only a small fraction of the cosmic budget, dark matter is several times more abundant, and dark energy dominates everything on the largest scales. A radio telescope tuned to microwaves had become a kind of cosmic birth certificate, stamped 380,000 years after the beginning. Explosions added their own surprises. Gamma-ray bursts were first detected by military satellites in the 1960s as mysterious flashes of high-energy radiation from random directions. For years, no one knew whether they were local or distant. The key was to catch one in the act with a telescope that could pinpoint its afterglow in visible light and then take a spectrum. When that finally happened in the 1990s, the redshifts showed that many bursts were billions of light years away. That meant they were unimaginably powerful, the death cries of massive stars or the mergers of compact objects, visible across most of the observable universe. Fast radio bursts repeated the pattern in miniature. Tiny blips of radio emission lasting only milliseconds, at first discovered almost by accident, turned out to come from galaxies far beyond the Milky Way. Pinning them down required networks of radio telescopes acting together to triangulate positions and then optical telescopes to identify host galaxies and measure redshifts. Each burst is a ping from the distant past, and the way their signals are smeared by plasma along the way is now being used to weigh the thin gas between galaxies. While all of that was unfolding, another revolution was happening closer to home: the discovery of exoplanets. At first, telescopes found oddities like a hot giant planet orbiting its star in just a few days, a configuration no one expected. Then dedicated searches using transit and radial velocity methods began to reveal thousands of planets around nearby stars. Missions like Kepler transformed a handful of cases into a statistical flood. We now know that most stars have planets and that many of those planets are roughly Earth-sized. Once again, time delay is quietly present in every detection. When a planet passes in front of its star, the tiny dip in brightness we measure today was imprinted on the star's light years ago. When a star's spectrum wobbles due to an orbiting planet, those subtle shifts carry the story of that orbit from years in the past. New telescopes now go further and analyse starlight that has filtered through alien atmospheres during transits, searching for gases that might hint at biology. Any such signal would be evidence of life as it was years or decades ago, by the time its photons reach our instruments. Then gravitational wave observatories joined the party. Instruments like LIGO do not use light, yet they behave like telescopes in a broader sense. They are tuned not to photons but to ripples in space-time itself. When LIGO detected its first black hole merger, it was hearing vibrations from an event that happened more than 1 billion years ago. Each detection is a message from the past about how massive objects collide and merge, and when those detections are combined with follow-up observations by traditional telescopes, as with the famous neutron star merger in 2017, we get a multi-messenger view. Light, gravitational waves, and sometimes neutrinos, all carrying records of the same ancient event through different channels. Dark matter too was dragged from speculation into necessity by telescopes. Vera Rubin and Kent Ford measured how fast stars and gas rotate in spiral galaxies and found that outer regions were moving too quickly to be held by the gravity of visible matter alone. Later, Hubble images of gravitational lensing by clusters showed that enormous amounts of invisible mass were bending light from background galaxies. Time-delayed photons, bent along curved paths, revealed halos of matter that do not shine. Put together with cosmic web maps and cosmic microwave background data, the case for dark matter became overwhelming. All of these discoveries share a theme. They were not made by one lucky snapshot or a single clever equation. They emerge from decades of telescopes patiently staring at distant objects, cataloguing their ancient light and letting patterns accumulate. Expansion, acceleration, invisible mass, planets everywhere, violent explosions, and ripples in space-time itself all came into focus because we learned how to read the past encoded in that light. In the next part, we will pivot from what telescopes have shown us about the universe to what that means for life elsewhere. We will ask what it really means to search for other worlds and other minds when every signal we detect is already a relic from years, centuries, or even millennia ago. Once you realize telescopes are time machines, the search for life beyond Earth starts to feel very different. We are not just looking for other worlds, we are looking for other histories. Every planet we detect, every atmosphere we analyze, every possible signal we pick up is already old when it reaches us. If we ever find life out there, the first thing we will know about it is that it existed some time ago. Maybe years ago, maybe centuries ago, maybe when our ancestors were chiseling stone or still climbing trees. The modern hunt for other worlds really took off in the 1990s, when telescopes first found planets orbiting normal stars. The methods were clever but simple. One approach, called the radial velocity method, watched for tiny wobbles in a star's spectrum as an orbiting planet tugged it back and forth. Another, the transit method, stared at thousands of stars and looked for minuscule dips in brightness when a planet crossed the face of its star from our point of view. In both cases, the story is the same. The light we measure today carries the imprint of motion or dimming that actually happened years before, when that starlight left on its way to us. Space missions like Kepler and the Transiting Exoplanet Survey, a satellite turned these tricks into planet factories. They recorded light curves, brightness over time for hundreds of thousands of stars. Regular little dips in those curves told us that planets were passing in front of their stars again and again. From the size of the dip and the time between repeats, you can work out the planet's size and orbit. What emerged was startling. Planets are not rare exceptions, they are the rule. Most stars have them, and many have multiple worlds. Among those worlds are some that orbit in what we call the habitable zone. That is the not too hot, not too cold distance where liquid water could exist on a rocky surface. Finding a planet in that zone does not guarantee oceans or life, but it makes them possible. When we hear about an Earth-sized planet in a habitable zone 30 or 100 light-years away, it is tempting to imagine it as a place right now. Forests, skies, maybe cities. But remember the delay. If that planet is 100 light-years away, the light we see left in the 1920s. Any life we infer from that light is life from a century ago. We are always catching up, never current. The next step in this search is not just counting planets, but reading their atmospheres. When a planet transits its star, a small fraction of starlight filters through the thin shell of gas around it. Different molecules absorb specific wavelengths, leaving faint fingerprints in the spectrum. With a powerful enough telescope and a stable spectrograph, you can detect those fingerprints. So far, most of the atmospheres we have probed belong to hot giant planets because they are large and easy targets. We have already found water vapor, carbon dioxide, methane, and other gases in those alien skies. The real dream is to apply the same technique to smaller, cooler, rocky planets. There, certain combinations of gases might hint at biology. On Earth, oxygen in our atmosphere is constantly replenished by photosynthesis. Without life, it would react away. Methane is produced by both life and geology, but in our air it is quickly destroyed by chemistry and sunlight, so its presence also implies steady replenishment. If we see strong oxygen and methane together, in the atmosphere of a rocky planet in a habitable zone, that would be difficult to explain without some ongoing source. It would not be proof of life, but it would be a very loud whisper. Here the time travel angle hits again. Suppose a future telescope around the year 2040 looks at a planet 30 light-years away and finds a spectrum rich in oxygen and subtle hints of methane. That would be the atmosphere of that planet as it was in about 1990, 10 years after the launch of the Hubble Space Telescope. Whatever is living there today, in that planet's own present, has evolved through another 3 decades of history that we cannot yet see. Our discovery is always lagging. We will never catch up to their now, any more than they could ever see us as we are the moment they start observing. The search for extraterrestrial intelligence, often shortened to SETI, leans into this idea even more. Radio telescopes and increasingly optical surveys listen for signals that might be artificial. Narrowband radio tones, pulsed lasers, or other patterns that are hard to explain by natural astrophysical processes. Any such signal would be a message from the past. A beacon coming from 1,000 light-years away would be broadcasting a 1,000-years-old story. Medieval Europe on our timeline. Whatever civilization sent it has had a millennium to change, flourish, decline, or vanish since those waves left. Even if we reply, the conversation is hugely stretched. A planet 100 light-years away sends a signal we detect today. That signal left when our great-grandparents were children. We send a reply now. It arrives there in their far future, long after the people who built the original transmitter are gone. Then any answer comes back to our great-grandchildren. This is not chat. It is correspondence across eras, more like reading carved inscriptions than talking in real time. Some scientists think about technosignatures, broader ways to detect technology, rather than just deliberate beacons. Atmospheric pollution that would be hard to produce without industry. Strange megastructures around stars that dim and brighten in odd ways. Waste heat from large-scale energy use. Again, telescopes are the only tools we have to search for these. They gather light from distant stars and pass it through this mental filter of what might look unnatural. But whatever we find, if we ever do, will be a frozen record. A civilization that built giant structures 1 million light-years away would show us its ambition from 1 million years ago. The era of their message and the era of our response could be separated by longer than human beings have existed as a species. Even without intelligent life, telescopes let us think about how life itself might spread in time. The idea of panspermia suggests that microscopic organisms could ride rocks blasted off one world and eventually seed another. If that happens, the life we detect on some distant planet might share origins with life somewhere else, millions of years earlier. We would be seeing descendants, not a fresh start. Spectra of atmospheres and reflections off surfaces would not just hint at chemistry, but at a lineage that has wandered across space and time. The moving, habitable zone around a star adds another wrinkle. Stars brighten as they age, so the belt where liquid water is comfortable slowly moves outward. A planet can spend billions of years in that zone, then drift out of it or be left behind as its star changes. Telescopes cannot track a single planet through that whole evolution, but by observing many stars of different ages with planets at different distances, we can reconstruct the sequence. Every world we see in a habitable zone is in that zone for a finite window. We are catching that window at one moment long after the relevant photons left. Future observatories like the proposed Habitable Worlds Observatory aim to go further and directly image Earth-sized planets around nearby stars. These would not be just dips in light, but tiny separate points, maybe even faint disks, where we could see seasons and weather patterns through changes over time. Still, every frame would be delayed. A future image of a nearby Earth twin might show continents, clouds, perhaps even hints of vegetation and colour variations, but those patterns and any life responsible for them would all be from decades in that planet's past. It would feel like a live view, yet be as historical as an old photograph. Seen this way, the search for life is not about synchronizing with other beings in some grand present. It is about archaeology at cosmic distances. We are digging through layers of old light, looking for fossils written in spectra and flickers, trying to piece together stories of biology and technology that played out far away long ago. If someone out there is doing the same with our light, they see a younger Earth, a younger civilization, and they face the same question we do. Are the senders of this light still there now? In the next part, we will pivot from life back to technique and talk about how astronomers use long-time baselines, messy archives, and multi-messenger observations to squeeze even more history out of telescopes. Variable stars, pulsars, supernova archives, gravitational wave timing, all of them show that once you accept the delay, you can turn it into a precision tool for probing both astrophysics and the nature of time itself. By now, the delay built into every telescope image might feel like a frustrating limitation. We never see anything as it is, only as it was, but astronomers have learned to flip that around. The delay is not just a handicap, it is a measuring tool. If you treat the sky like a giant lab experiment that has been running for centuries, then every old plate, every digitized image, every repeat observation becomes another data point in a long-running time series. The universe has been performing. Telescopes are just learning how to read the recordings. Variable stars are one of the clearest examples. Stars like Cepheid variables and Mira-type giants change their brightness over days, weeks, or months. Early observers simply noticed that some stars appeared and disappeared, or slowly waxed and waned. With telescopes and careful records, astronomers turned that into precise light curves. Delta Cephei, for instance, has been monitored since the 1800s. Mira has records going back even further. Each generation adds more measurements to the same repeating pattern. When modern astronomers digitize old photographic plates and combine them with fresh electronic data, they get light curves that span more than a century. Over that span, tiny drifts in the pulsation period and amplitude become visible. Those drifts reveal slow structural changes inside the star, changes no human could see in a single lifetime. The light travel time delay is baked in, but it does not matter, because what matters is relative change. The star is a clock, and telescopes are reading its tick over centuries. Supernova light echoes push the idea of delay even further. When a star explodes, the first burst of light travels straight to us, arriving after whatever number of years fit its distance. But some of that light takes longer routes. It spreads outward, hits distant dust clouds, and reflects toward Earth. Those reflected paths are longer, which means the echo arrives years, decades, or even centuries after the original flash. Telescopes can capture these echoes as faint expanding rings or patches around the supernova site. This is more than a visual curiosity. That delayed light still carries the spectrum of the original explosion. In a few cases, astronomers have used light echoes to take spectra of supernovae that were seen by observers in the 1600s or earlier. Ancient sketches and written reports tell us a bright new star appeared. Modern telescopes catch the echoing light, spread it into a spectrum and reveal what type of supernova it was. It is like discovering that a historical painting also contains a hidden audio recording you can play back. Pulsars turn delay into a precision test of physics. A pulsar is a rapidly spinning neutron star that sweeps beams of radiation past us like a lighthouse. Radio telescopes record each pulse as a tick. Some pulsars spin hundreds of times per second with astonishing regularity. Over years of monitoring, the arrival times of those pulses can be predicted down to microseconds. Any deviation from that prediction must come from something interesting. In binary systems where a pulsar orbits another star, those deviations track the orbit in exquisite detail. One famous case, a binary pulsar discovered in the 1970s, showed that the orbit was slowly shrinking. The two stars were spiraling together as they lost energy to gravitational waves exactly as general relativity predicts. The amount of orbital decay matched Einstein's equations. A radio telescope, a stopwatch, and decades of delay turned into a test of gravity no lab on Earth could match. Scale that idea up and you get pulsar timing arrays. Instead of one pulsar, you monitor dozens scattered across the sky. Each one is a clock. As very long wavelength gravitational waves pass through the galaxy, they subtly stretch and squeeze spacetime, changing the arrival times of pulses in a correlated way. The effect is tiny, but with many pulsars and many years of data, it becomes detectable. Recently, collaborations using telescopes on several continents announced evidence for a background of gravitational waves from giant black hole binaries humming across the universe. That detection depended entirely on the patient use of delay as a signal. Gravitational lens time delays offer another clever trick. When a massive galaxy or cluster sits directly in front of a more distant quasar, its gravity bends the background light into multiple paths. We see several images of the same quasar at different positions on the sky. If the quasar brightens or flickers, that change appears in each image at different times, because the light paths have different lengths. Telescopes can monitor those images and measure the delays between brightness variations. Those delays are not just curiosities, they encode the geometry of the universe. By combining the lens mass model with the measured delays, astronomers can estimate the overall expansion rate of space. It is yet another way that listening carefully to when photons arrive, not just where they came from, turns delay into data. A flickering quasar billions of light years away becomes a cosmic stopwatch. Time domain surveys extend this approach to the whole sky. Telescopes like the Zwicky Transient Facility photograph huge areas of sky night after night, looking for anything that changes. New supernovae, flaring stars, asteroids, variable nuclei, all of them show up as differences between images taken days or weeks apart. Soon, the Vera Rubin Observatory will take this to an extreme, imaging the visible sky every few nights for years. Each new image is delayed light, but what matters is that the delay is consistent. By comparing frames, astronomers build movies of how the sky changes. Sudden eruptions can be caught early. Slow variations can be tracked for years. When an event like a neutron star merger is first detected by a gravitational wave observatory, telescopes can rush to the location and watch its light evolve. That evolution, combined with the time of the wave arrival, reveals the physics of dense matter and heavy elementary creation. Delay becomes the glue that ties different messengers together. Archive mining is another quiet revolution. Old telescope plates and images were once used for individual projects, then filed away. Now they are being digitized and searched for patterns with modern algorithms. When a new supernova explodes, astronomers often go back through archival data to see if the progenitor star was ever visible. When a strange variable is discovered, decades of old images can show whether it has always behaved that way. The sky has been under surveillance for longer than we remember, and everything recorded is a delayed report. Even in more everyday applications, delay is a tool. Exoplanet hunters use transit timing variations, tiny shifts in when a planet crosses its star, to infer the presence of additional unseen planets tugging on its orbit. Astrometric missions like Gaia use repeated measurements of stellar positions over years to detect subtle wobbles caused by orbiting companions. In both cases, the story is told not by a single snapshot, but by the way positions and times change across many snapshots, all delayed but all ordered. Once you accept that the universe always shows you its past, it becomes natural to design experiments that lean into that fact. Telescopes are no longer just cameras pointed outward. They are chronographs, instruments that measure how processes unfold on timescales far beyond a human life. By stacking delays from many sources, astronomers turn the finite speed of light into a ruler, a clock, and a probe of fundamental physics. In the next part, we will step back from the technical details and ask what this all means for our ideas of time, reality, and our place in the cosmos. If everything we see is already gone, what does it really mean to live in the present? And how does knowing the universe as a history rather than a snapshot change the way we think about ourselves? Stand outside on a clear night, look up, and your brain plays a little trick on you. It feels like you're seeing the universe now, stars above you now, the Milky Way arching overhead now. But by this point in our journey, you know that is not what is really happening. You're standing in the present, but your eyes and every telescope ever built are filled with messages from different yesterdays. The sky is not a picture of where things are. It is a collage of where things were. Once you let that sink in, some very deep questions sneak in with it. Start with something simple. What is the present? For you, it is this moment as you watch this video or listen to this voice. For someone on a planet in the Andromeda galaxy 2.5 million light-years away, their present is 2.5 million years out of sync with ours in terms of what we can see. When they look at us through their telescopes, they see Earth in a far more primitive state than we know it to be. When we look at them, we see their distant past. The idea of one universal now stretching across the cosmos falls apart. Einstein's relativity sharpened that idea. It tells us that different observers moving relative to one another slice space-time into past, present, and future in different ways. There is no cosmic master clock that declares this is the exact moment everywhere. Telescopes make this real. Every observation is a slice through space-time along your light cone, the surface traced out by all the light that could have reached you by now. Everything outside that cone exists in some sense, but is invisible to you for the moment. Not because it is hidden behind a wall, but because it is simply too soon for its light to arrive. This is a strange way to live. All of our intuition is wired for local physics. I flip a switch, the light turns on. I drop a ball, it falls. Cause and effect line up in a neat chain. The cosmos laughs at that simplicity. Events in distant galaxies are unfolding right now in their own local present, but they are absolutely disconnected from us in any practical sense. The consequences of those events will not wash over us for millions or billions of years, if ever. When telescopes catch a supernova in a galaxy 100 million light-years away, that star lived and died before mammals existed on Earth. There is something humbling about this. We like to imagine ourselves at the center of things, not in the literal medieval sense maybe, but in a quieter psychological way. As if the universe is happening around us, and we are watching it live. Telescopes remind us that we are late arrivals to an already very old party. The universe has been doing its thing for more than 13 billion years. Whole galaxies have formed, merged, and faded long before our planet solidified. When we observe them, we are reading their fossil record, not live news, yet this is not depressing. It is strangely empowering. Despite being tiny and late, we have figured out how to read the archive. We have decoded the patterns in ancient light well enough to reconstruct a story that spans almost the entire age of the universe. We can say when stars first formed, when galaxies were most active, when expansion began accelerating, how much invisible matter there is, and even what the baby universe looked like before there were stars at all. That is a staggering leap for a species that evolved on a small wet rock orbiting an ordinary star. It also changes the way we think about questions that go beyond science. For most of human history, the sky was a symbol of permanence. Stars were the fixed backdrop against which the drama of human life played out. Now telescopes tell us those stars are anything but fixed. They are born, evolve, and die. The Milky Way itself is changing, interacting with its neighbours, slowly spiralling into a future merger with Andromeda. There is no eternal stage. Everything we can see is part of an evolving story. Education takes on a different flavour in this light. When a student learns about the Andromeda galaxy, they are not just learning about a pretty spiral in a textbook. They are learning that there is no way for us to see Andromeda as it truly is right now from our frame of reference. All of our data come from light that left millions of years ago. That simple fact forces you to confront causality, relativity, and the limits of observation. The idea of an objective present dissolves into a more subtle picture where each observer carries their own light, cone, and their own accessible slice of cosmic history. There are personal implications too. On human scales, the speed of light is effectively infinite. We do not notice the delay between seeing a friend across the room and their actual present state, but telescopes teach us that delay is always there and grows with distance. If communication with other civilizations is ever possible, it will be communication with their past and they with ours. We will never share a real-time conversation with another intelligence among the stars. At best, we will exchange letters written across centuries and millennia. That forces a different way of thinking about connection. Instead of dialogue, we have archaeology at a distance. If we detect biosignatures on a planet 100 light-years away, we will know that life existed there 100 years ago. We will not know if it has since flourished, collapsed, or transformed. If someone there points a telescope at Earth right now, they see our own world as it was in the early 1900s. Steamships were early airplanes, no internet, no deep space probes. Their image of us and our image of them are both stuck in their respective pasts. In a way, telescopes teach patience. They remind us that the universe does not work on human timetables. Processes that matter most in cosmology take millions or billions of years. Star formation, galaxy mergers, chemical enrichment, all of them unfold so slowly that no single generation can watch more than a tiny slice. Yet by carefully stitching together delayed signals from different distances and centuries of local records, we can still see the arc. It is an antidote to the illusion that if we do not see change instantly, nothing is happening. This perspective can also soften the edges of existential angst. When you realize that the calcium in your bones was forged in long-dead stars, that the atoms making up your body spent billions of years wandering through space before ending up here, and that the night sky is not a ceiling but a time-layered archive your sense of self stretches, you are not just a person in a particular year. You are a local configuration of cosmic history, briefly coherent, capable of turning around and understanding the story that made you. Telescopes are the tools that let that understanding crystallize. There is one more twist. The very fact that we can reconstruct this history depends on the laws of physics being reliable across time and space. Photons preserve their basic properties over billions of years. Gravity behaves consistently enough that dark matter halos and galaxy clustering follow predictable patterns. If the rules were wildly different in different eras, telescopes would show us chaos. Instead, they show us an ordered universe with a deep past we can read. That regularity is part of why the scientific method works at all on cosmic scales. In the final part of this journey, we will look ahead. We will ask what the next generations of telescopes might reveal, how far back in time we can realistically hope to see, and what new paradoxes and surprises might be waiting in the ancient light that has not yet reached us. The archive is still being written. Our instruments are getting better at reading it. The story of telescopes as windows into the past is nowhere near finished. We have spent this whole journey looking backward, back to exploding stars, colliding galaxies, the first atoms, even the baby picture of the universe itself. So now comes the obvious question. How much deeper can we push? How far back in time can telescopes really take us? And what does it mean that the greatest discoveries may still be hiding in light that has not even arrived yet? Right now, we live in a golden age of telescopes. Space observatories like Hubble and Webb have already changed what we thought was possible. Webb in particular was built almost perfectly for time travel. It is tuned to infrared light, the stretched-out glow of galaxies whose light has been pulled to longer wavelengths by billions of years of cosmic expansion. When Webb stares into a patch of sky that looks empty from Earth, it finds tiny red smudges that are actually young galaxies only a few 100 million years after the beginning. In other words, we are finally watching the universe in its cosmic childhood instead of only in middle age. On the ground, a new generation of giant mirrors is rising. The extremely large telescope in Chile, with a primary mirror nearly 40 meters across assembled from hundreds of segments, will gather more light than any optical telescope in history. The Giant Magellan Telescope and the 30-meter telescope are following similar strategies. With adaptive optics to cancel out the atmosphere, these enormous eyes will resolve stars and structures in distant galaxies that are now just blurs. They will be able to pick apart star-forming regions in galaxies billions of light years away and do detailed spectroscopy of exoplanet atmospheres around nearby stars. New survey telescopes are rewriting how we watch the sky change over time. The Vera Rubin Observatory will scan the visible sky every few nights for years on end. That means it will not just catch rare events like supernovae or tidal disruption flares when a star is torn apart by a black hole. It will watch them evolve frame by frame. It will trace how variable stars drift, how asteroids move, how distant quasars flicker. All of that is delayed light, but the delays are known and ordered, so astronomers can turn those repeated snapshots into precise histories. Space-based survey missions will add their own chapters. The Roman Space Telescope will conduct huge infrared surveys, mapping dark matter through weak lensing and tracking how structure grew across billions of years. It will find thousands of distant galaxies at key moments in cosmic history and discover new exoplanets through microlensing, where the gravity of a foreground star briefly magnifies a more distant one. Each of those detections is a little knot of history teased out from temporarily warped starlight. Then there is the frontier that feels almost like science fiction. Space interferometers, fleets of telescopes flying in formation, combining their light to act as one gigantic instrument. In principle, a group of spacecraft spread out over thousands of kilometers could resolve details on nearby exoplanets that are completely invisible today. Not just a pale dot, but hints of continents, oceans, maybe seasonal changes in color that could indicate vegetation. Every image would still be decades old by the time it reached us, but that would hardly diminish the impact of actually seeing another living world. Other messengers are getting upgrades as well. Next-generation gravitational wave detectors on Earth, such as planned underground observatories, will be sensitive to many more black hole and neutron star mergers out to much greater distances. The space mission LISA will listen for lower frequency waves from supermassive black hole pairs as entire galaxies merge. Each detection is an ancient vibration of space-time, carrying news of events that happened billions of years ago. Combined with traditional telescopes, these signals will let us reconstruct some of the most violent episodes in cosmic history in more detail than we ever thought possible. Neutrino observatories are slowly stretching their reach too. Instruments like IceCube already catch high-energy neutrinos from distant galaxies, ghostly particles that pass almost unhindered through matter. Future detectors tuned to much lower energies might one day detect a cosmic neutrino background, a relic from roughly 1 second after the beginning. That would push our observational window far earlier than any electromagnetic telescope can go. At that point, we would not just be watching the universe as a toddler, we would be listening in on its first heartbeat. There are even ideas for building radio telescopes on the far side of the moon, where Earth's radio chatter cannot interfere. A large low-frequency array there could pick up the soft glow of neutral hydrogen from the cosmic dark ages, the period before the first stars turned on. That would fill in yet another missing chapter between the smooth microwave background and the bright galaxies Webb is now seeing. Each new band of the spectrum we open tells us about a different era in the past, and the moon happens to be a very quiet place to listen. Of course, there are limits. No matter how powerful our telescopes become, no signal can bring us information from before the universe became transparent to that type of messenger. For light, the cosmic microwave background is the wall. For neutrinos or gravitational waves, the wall lies even earlier, but it is still there. On the other end, dark energy is gently pushing distant regions away so quickly that their light will never reach us at all. There are galaxies whose present and future will remain forever outside our observable universe. Their histories are real, but we will never read them. Our cosmic archive has edges baked into the structure of space-time itself. There are also down-to-earth challenges. Light pollution from cities and swarms of bright satellites make ground-based astronomy harder. Funding multi-billion-dollar observatories demands patience and political will that can waver over decades. Data from new surveys are so vast that we need machine learning to sift them, and we worry about missing the unexpected, because our algorithms were trained on what we already know. Calibration and maintenance become labyrinthine tasks when an instrument is meant to operate in deep space for 20 years without a repair visit. The future of time travel by telescope is not guaranteed. It has to be built, protected, and justified. Yet the momentum is real. Around the world, teams are aligning mirrors, cooling detectors, writing code, and designing rockets that will carry the next generations of eyes into orbit. The universe, for its part, is still sending photons, neutrinos, and gravitational waves from every era of its history. Most of that ancient rain will never hit anything. A tiny fraction will find our sensors, an even smaller fraction will be recognized, understood, and folded into our shared story about where we came from. Here is the quiet, beautiful part. You do not need a billion-dollar facility to feel any of this. A backyard telescope aimed at Jupiter is already a time machine, the light bouncing off its clouds left tens of minutes ago. A glimpse of the Andromeda galaxy in binoculars shows you a swirl of stars whose photons began travelling when early humans had no writing, no metal, no science. No, even unaided eyes looking at the bright star Sirius are seeing it as it was more than 8 years in the past. Once you know that, the night sky stops being static decoration and becomes a living archive. Telescopes, from the simplest glass tube to the most complex space observatory, all do the same astonishing thing. They turn distance into time. They let a fragile species on a small planet read the universe's diary page by page, scene by scene, across billions of years. They show us that the past is not entirely gone, that it lingers in the light still crossing the void waiting to be caught. And they remind us that we too are writing our own entry in that diary, broadcasting our existence outward on expanding spheres of radio waves and scattered sunlight. So the next time you see an image from Webb or Hubble, or you step outside and look up, remember what you are really seeing. Not things as they are, but as they were. Not a static dome, but layers of history stacked across the sky. We are latecomers who learn to build tools that borrow light from long ago and far away and use it to understand everything from the birth of atoms to the fate of galaxies. That might be the most extraordinary trick any species has ever pulled off.